All right, so as we ended yesterday, I said that, or what we're going to be doing today is I'm going to go back over the beginning of section C to just reinforce what we covered yesterday. See if anybody has any questions. We're going to finish up section C. And then I'm going to really review back over the whole section, meaning sections A, B, and C, or probably not C again, because we'll just have done that. But I'll go back over A and B and see if there's any questions and really that is it for today. Tomorrow, the final is open for you to be able to take. And on Friday and Monday, you're to be online completing all the material, the online material. Quite a few people have got a lot done, and well, it's about half and half almost. Half the people did quite a bit, the other half haven't even started yet. So keep in mind, it does need to be done on Monday, or by the end of Monday. All right. Also, landing gear does begin on Monday, but we will not have our Zoom lecture until Tuesday morning. All right. At that time, I will let you know when we're coming in. Right now, I'm kind of leaning to let's lecture on Tuesday via Zoom in landing gear, and on Wednesday, we will come in and do projects, possibly even Thursday to do projects, and then back online on Friday, and we'll work it from there. All right. Are we all good with that?
Yep.
Good.
Okay. All right. So to go back over section C, and I won't try to drag this out too long. We need to remember that we have what is known as an autogyro. What is special about an autogyro? The main rotor is the lifting device. The thing is that the main rotor is not powered by an engine. It is powered by the aerodynamic forces flowing through the rotor. So it does what is referred to as auto rotate. Now, as long as the aircraft is moving forward, the rotor blades will spin. As long as they're spinning fast enough, the aircraft can ascend or they can descend, okay? Or they can stay in level flight. But we have to understand that the limitations to an autogyro is that from the ground, it just can't go straight up. It can somewhat go straight down, but it has to have some forward motion, but it just can't go straight up, and it cannot hover. It always has to be moving forward, okay? And that is an autogyro, that the main rotor is not powered. It does have an engine, and the engine is there to produce forward thrust. The autogyro may have a pitchable rotor, or a tiltable rotor, or the rotor blades can be pitched, or as this one has, it could actually have conventional control surfaces such as ailerons, rudders, and an elevator. Most autogyros do have a rudder though, okay? Even if they don't have ailerons or elevators. From there, we went on to the actual helicopters, and that is one that has a powered rotor blade, okay? Now, here is a single rotor system, which is majority of helicopters, but some helicopters have dual rotors. Now, in this case, they are intermixing, but one famous helicopter that has dual rotors is the Chinook, okay? When they have the two rotors, they don't or will not have a tail rotor. Okay, whereas the single rotor systems will always have then a tail rotor. But that ain't always true. There are helicopters now that have no tail rotor, and those are called no cars. And we will be talking about that later on today. All right. Now, there are different types of rotor systems. Early days, they made what was known as a rigid rotor. A rigid rotor only allowed the blade to pitch, okay? But as we seen yesterday, there's a lot of other forces. There's forces that try to bend the flaps or bend the rotor blade up and down, which then makes the blades want to lead and lag. So we have these blades that have all these forces that are trying to make them go up and down, lead and lag, and then we also need to pitch the blades, okay? So the rigid rotor, when they first were built, they were so rigid that they could only pitch. All those forces would fatigue the rotor blades, and there was a lot of rotor blade failures. Today, we have gone back to, and some helicopters are referred to as rigid rotor, but what they have come up with is what's known as an elastomer bearing. All that means is a big rubber block, and the rubber block allows the blades to flap and to lead and lag. But before that was invented, I'll say, or brought into use, the step was to go to what's known as a semi-rigid rotor blade. A semi-rigid rotor blade will have two rotor blades that are rigidly connected to each other, but they're attached to the center mast with what is known as a teetering hinge. Okay, it's this one. And here we have the teetering hinge. The important thing about the semi-rigid is now that each blade can pitch up and down, but they also can teeter up and down, or we can refer to it as flapping. Now, they can't independently flap. It's when one goes up, the other one goes down. An important fact is that the teetering hinge is above the center line of the rotor blades. This is what's known, or is said, that the rotor blade is under slump. Now, we know that because of yesterday. Why is the semi-rigid rotor blade under slump? And it's to help minimize the Coriolis effect. The Coriolis effect basically is that as a rotating mass gets closer to the center of rotation, the speed doesn't change, but the RPMs do. And the reason for that is, as we did yesterday, if we have a big circle, right? If we're going around here, one revolution and 1 RPM, right? If the center of mass gets closer, the speed hasn't changed, but we now have to go 2 revolutions per minute because the velocity has not changed. So when the blades flap up, they have a tendency to get closer to the center mass or the center of rotation. That has a tendency for the blade to want to lead, whereas the blade that's flapping down will try to lag. So to try to minimize these forces, they underslung the rotor blade so that when the blade teeters up, it actually moves towards the high one, meaning it moves kind of away from the center of mass. Now, it kind of equals out. Hey, the blade flapping up is trying to get closer to the center of mass, but because it's underslung, it stays roughly the same distance away. All right, so keep that in mind. How does a semi-rigid rotor blade minimize the Coriolis effect? And the answer would be under slump. Now, if we have multiple blades, more than two, then most aircraft or helicopters are what's known as fully articulating. This is where the engineers have a pitching hinge. They have a hinge so that the blades can flap up and down, but also a separate hinge that allows the blades to lead and lag. That way the blade can do whatever it needs to do to keep balance. Is there any questions on the three?
No.
If not, I'll continue on. All right. The next little section talks about the forces acting on the rotor blade. And of course, yes, we have gravity. That's weird. Okay, we have gravity, which basically makes the rotor blades droop towards the ground. We have centrifugal force that's trying to pull the blades out from the center of rotation, okay? And these are very, very strong forces. We also have lift acting on the rotor blades, which then overcomes gravity and they have a tendency to bend upward. Okay? And then we have the two gyroscopic, well, I don't want to skip anything. So those are those that helicopter rotor blades are generally of the symmetrical shape. And the reason for this is that it puts less strain or vibration within the rotor blades. And the reason is because with a symmetrical airfoil, that when the angle of attack changes, the center of pressure or lift does not change very much. It does, we can say that it doesn't change. Therefore, does not put any additional twisting force to the rotor blade. Whereas an asymmetrical airfoil, as the angle of attack changes, so does the center of pressure or lift. They're interchangeable. Which then, as the angle of attack increases, the center of pressure moves forward, which then tries to increase the angle of attack. And when the angle of attack decreases, the center of travel moves back, reducing that force, trying to increase the angle of attack. Whereas the symmetrical airfoil stays the same and thus puts no additional load on the rotor blade. The two gyroscopic forces, the one that says that a spinning object tries to stay in that plane of rotation is known as rigidity in space. Whereas precession says that a force acting on a spinning object does not act at the point at which the force is applied, but acts 90 degrees in the direction of rotation. So I don't have the wheel of death with me, but if we had a spinning wheel that's spinning towards you and we try to tip it over, what happens? The front of the wheel would turn to the left. If anybody rides a motorcycle, they pretty much know this. When you're riding a motorcycle, especially when you're going rather quickly, you don't, when you want to make a left turn, you just don't turn the wheel. What you do is you lean into the turn. When you lean into, I'll get the wheel of death. I know you want it. Hey, anytime I get to play with the wheel of death, I'm going to do it. So if that's the front wheel of a motorcycle, if I try to turn, just turn to the left, you can see I would wipe out very quickly. Whereas if I lean into the turn, see how the wheel kind of turns in the direction that I want to go. and thus makes it much easier to control and balance out. All we have to do is kind of lean into it. All right. Is there any questions on the two gyroscopic forces?
No. No question.
Nope.
Okay, okay. Just keep in mind, you might see a question. What type of gyroscopic force says that the force applied actually is at 90 degrees in the direction of rotation? That's precession. The tendency for a spinning object to stay in the plane of rotation is rigidity in space. Okay. We already kind of hit upon it, but the next one is what's known as the Coriolis effect. As I said, as say a rotor blade flaps up, it gets closer to the center of rotation. So that blade would want to advance or lead. If a blade is flapping down, the center of mass is getting further away from the center of rotation, and then is said to lag. As we said, a semi-rigid rotor blade is designed to be underslung so that it minimizes this effect. A fully articulating rotor blade doesn't really try to minimize the Coriolis effect. It has a lead and lag hinge so that the blades can move forward and aft. All right. We then went into the helicopter flight conditions, hovering flight. As I said, in hovering flight, the big problem was this. There's torque on the helicopter that as we spin the rotor blades counterclockwise, the body of the helicopter wants to turn clockwise, or the nose wants to go to the right. Igor Sikorsky is the person that created the anti-torque rotor. And the anti-torque rotor, by use of the anti-torque pedals, we can call them rudder pedals because a lot of people do, okay, are designed to increase or decrease the thrust of the tail rotor. So it's set up so that when the rudder pedals are neutral, it puts out enough thrust to keep the nose straight. The problem is the torque rotor is pushing the tail to the right, and the torque of the rotor blade is pushing the nose to the right, and thus the helicopter had a tendency to drift to the right. To compensate for that, they could do two things. One, they could tilt the rotor to the left so that it balances out that drift, or when they're rigging the rotor blades, the advancing blade has a slightly higher angle of attack than the retreating blade, and thus keeps the aircraft straight. And that was those two things. Next, we talked about the density altitude. The density altitude is the density of the air at any given altitude. As we go up in the air, we got to understand that the density decreases. Because of this, a helicopter has to push more air down as they go up higher and higher to maintain the displacement. Remember Newton's third law, for every action there's an equal and opposite reaction. So if the helicopter weighs 1,000 pounds near the ground, all it has to do is displace 1,000 units of air, because 1 unit equals 1 pound for this example. As we go up, to about 18,000 feet, at 18,000 feet, the density of air is about 1/2 of what it is at sea level. So at 18,000 feet, the helicopter would now have to push down 2,000 units of air, because each unit of air only weighs 1/2 pound. And so we end up getting into limits of how much volume of air we can push down. And thus, only a certain height would we be able to fly. That was density of altitude. Next, we talked about the ground effect, okay? And the terminology is OGE and IGE. IGE stands for in ground effect. OGE is out of ground effect. And a helicopter is said to be in ground effect when it's within one diameter of the rotor blade. And the helicopter can produce more lift when it's in ground effect than when it's out of ground effect. And the whole reason is because of the vertical velocity of the air going through the rotor blades, okay? Figure when the aircraft is out of ground effect, it's pushing air down. So we have what's known as a vertical component of that air. And this vertical component decreases the angle of attack that the rotor blades are hitting the air. Thus, with lift, remember, if the angle of attack decreases, the amount of lift is decreased. When we get close to the ground within one diameter, you probably can't see that, okay? What happens is the air coming down hits the ground and has to slow down to make a turn. Because the vertical velocity of the air has decreased, the angle of attack of the rotor blades has increased, thus providing more lift. Are we good there?
Good.
Yes.
Okay. Now, there's what's known as translational lift, and that is the term where, say we wanted to take a heavy load, heavier than what we could do straight up and fly or hover out of ground effect. So what we do is we lift the weight, keeping the helicopter in ground effect within one diameter of the rotor blade. Now, before we go out of ground effect, we now start flying forward. As we fly forward, the vertical velocity has decreased because we've increased the horizontal speed of the aircraft. This then increases the angle of attack, where now, as long as we're moving forward, we can carry that weight even when we're in or out of ground effect. We can't stop, we can't hover out of ground effect with the extra weight. When we want to come into land, we descend almost like a regular fixed wing aircraft. Now, when we come into ground effect, this is when we can hover and maneuver normally. The vertical ascent and descent, I believe we kind of, if we push more air down, meaning the weight of the air down more than the aircraft weighs, we go up. If we reduce the amount of lift, we come down. Pretty straightforward. The next one was forward flight, and the thing is known as what's called dissymmetry of lift. When the helicopter is flying forward, okay, the advancing blade is now traveling faster through the air than the retreating blade. And as we know from the lift formula, as velocity increases, so does lift. So on the advancing blade produces more lift than the retreating blade. And so what happens is the helicopter wants to roll over. To help prevent this, we allow the blades to do are to flap. So as the helicopter flies forward, the advancing blade flaps up. Now keep in mind, when that blade flaps up, the vertical velocity is said to increase, because if the air is pushing down at 100 and the blade flaps up at 100, it kind of cancels the two out, if you will, or cancels or increases to 200. Sorry. And whenever you have an increase of vertical velocity, you have a decrease in angle of attack. So keep in mind, questions for tomorrow. The blade that flaps up, does the angle of attack increase or decrease? And the answer is the angle of attack decreases. Now, on the other hand, the blade that now is flapping down has decreased the vertical velocity, and thus the angle of attack increases. By the advancing blade, reducing its lift, and this one increasing its lift, it now balances out compared to the forward velocity of the helicopter. Now there's a limitation to that, and that's known as a retreating blade stall. In a retreating blade stall, the helicopter is going so fast forward that the retreating blade has to flap down so much that that blade's angle of attack reaches its critical angle of attack. And thus we get what's called a retreating blade stall. Now, a retreating blade stall is said to occur at the 300 to 270 degree mark. Okay? Now, because of precession, the effect is not done to roll the aircraft off over to the left, but acts 90 degrees towards the tail. So in a retreating blade stall, does the nose go up or down? And the answer there is that the nose goes up because we lost the lift at the tail. So the helicopter would tail down or nose up. Any questions there?
No, sir.
No? Okay. All right, so we did that. We did the retreating blade stall and we did the translational lift. Next is the it's crazy, all the diagrams that they try to show, but for auto rotation, if we have an engine failure, the rotor blade will keep turning. It's on what's called a freewheeling unit. And what that means is that the engine can turn the rotor blades, but if the engine stops, the rotor blades keep on spinning. All right. So that way, if anything happens with the engine transmission, the rotor blades will freewheel. Okay. So if we have a power outage, okay, the pilot would kind of pitch the nose down. And as that happens, the air flowing over the rotor blades creates enough lift forward to keep the rotor blade spinning. Now, the pilot usually will move the collective down, which lowers the pitch of all the blades to gain as much momentum in the rotor blades as possible. By doing this, the outer portion of the rotor blade are traveling fast enough that they will actually create some lift and thus slow the descent down. Now, I'm just saying slow the descent down, not like a real gentle descent. It goes rather quickly. Okay? Now, the idea is to use the momentum of that rotor blade so that when they get to a specified height, the pilot then pulls up on the collective, increasing the blade angle of the rotor so that they can use the rotational speed and the higher angle of attack to then slow down the aircraft enough so no serious damage will be done to the aircraft once they land. And folks, that's what we covered yesterday. So before I continue on, is there any questions on that?
Yeah, I have a question.
Oh, yay!
For
Uh-oh. I can't hear you. I don't know what happened, Jaylene, but I can't hear you. Oh, that's sad. Are you still there, Jaylene? Somebody else speak so that I can tell if it's my
Hello,
computer.
hello.
Okay, Ilio there.
Yeah.
Yeah, we can hear you.
Yeah, we can hear you.
Okay,
Hey, Bob.
all right. I kind of see, I don't see Jaylene now.
Her internet probably died.
I gotta say, have you seen the commercial where the guy, like for the Lord of the Rings or something, and it's finally his turn and his internet breaks up? That's what just happened to Jamie.
I don't doubt it.
Yeah, all right, so hopefully she'll be able to get back on and fix that situation, because it was the only first time we had a question. Okay. To continue on, and then hopefully she'll be able to. I'm gonna turn on the light because I need to. I can't see with it. And this part's not so critical that you said, okay. That's so much better. All right. What we're talking about now is what's called rotorcraft controls. How do we control a helicopter? All right, early days, be it autogyros, even early helicopters, they had, basically there's three controls. You have the center stick, which is the cyclic. You have a side handle that goes up and down, which is called the collective. Okay, and then we have the rudder pedals that are officially known as the anti-torque pedals. The cyclic, when you push forward, back, left, right, the cyclic changes the pitch of the blades independently, okay? So if we want to make the helicopter go forward, we push the stick forward, the blades pitch as they should, so that the helicopter then tilts forward and flies forward, okay? If we go to the left, go to the right, those things will happen. The collective is used to increase the pitch of the blades collectively, meaning all together. So if we lift up on the collective, all the blades angles will increase, thus producing more lift. That makes us go up. If we push the collective down, we decrease the rotor blades angle and we produce less lift, and thus we come down. If we want to yaw to the right or to the left, we push on the anti-torque pedals to the right or to the left, which then increases or decreases the pitch of the tail rotor to then increase the anti-torque or to loosen, release that force so the torque of the rotor blades turns the nose of the helicopter to the right, okay? Now, early days, the cyclic was actually just connected directly to kind of the rotor itself and kind of the engine in it. And it was like, okay, I want to go forward. What it did was it actually tilted the whole rotor forward or tilted it to the right or to the left. So anytime I have the chance for the wheel of death, so it was like, here's the rotor blade, here's the cyclic. I tilt it forward, I go forward. I tilt it back, I go back. I tilt it to the left, to the right, and that's all it was a direct connection. The problem is, over time, you know, the rotor blades got larger, they spun, say, with more rigidity in space. And because of that, trying to move it got pretty much impossible for the pilot, and thus, you know, the advent of the pitchable and what we refer to as a swash plate. Okay, in that the cyclic and collective controls or the inputs from the pilot are sent to a device called a swash plate. Okay, and the swash plate then transfers that information or those inputs from the pilot via the cyclic and the collective to the rotating rotors. Okay, so what it is that we have two plates. And in between the plates is a bearing. So the bottom plate is stationary. What that means is it does not rotate. But we can tilt it in many places. Okay, we can tilt that plate. Okay, and the plate can go up and down. The plate on top of it is rotating with the rotor blades. So if we want or move the cyclic, then the top plate also follows what the bottom plate is doing, okay? So if we tilt it, then the plate moves and the rotor blade increases its pitch through these pitch lengths, okay? So figure if the swash plate tilts, the one that goes up, that blade's angle of attack generally will increase. It's one way to say it. It's not always true because it depends on how they design it and where they connect the pitch lengths to the rotor blades. But let's just say that it's easier for people to picture it. If the swash plate moves up, the pitch moves up, okay? So that tilts. Now, as the rotor blade turns, what then happens is the blade's turning, so any blade, let's say on the advancing side, that pitch would go up. The blades that are retreating, the blade angle is decreasing. The key thing that you need to know is this. What is the device that takes the input from the pilot and sends it to the rotor blades themselves? And that is what's known as the swash plate. If the pilot moves the collective up, the whole swash plate moves up, thus increasing the pitch of all the blades. And when it moves down, it decreases. And I do have some video online about the swash plate. It was really hard to find anything really good on the swash plate. In the past, what I've tried to describe it as, if anybody knows what a lazy Susan is, you know, a lot of times people have it, say, in the kitchen. Basically, it's one plate with a bearing and another plate, and then you can spin the top plate, and that's basically what a swash plate is. All right. Already talked about the collective pitch control, right? The throttle. The throttle for the engine is usually attached to the collective. And it's kind of like a motorcycle twist ring. As you twist the throttle, we increase the power of the engine. Now, the thing is a lot of times the throttle is also, or the power output of the engine is also connected to the collective as far as you increase the collective, what we have to understand is that the rotor blades, the pitch increases, which then puts more drag on the engine, okay? Meaning that the engine has a harder time to try to turn that rotor blade. So a lot of times when the collective is raised, not only does it increase the pitch of the blades, but it also increases the power output of the engine. We already talked about the cyclic pitch control. I don't think it, and some of this stuff, like they talk about, there's the collective, there's the cyclic. Here's kind of a question. Most pilots, most pilots in fixed wing, the pilot in command sits in the left seat. In helicopters, majority of the time, the pilot sits in the right seat. And, you know, I've had people ask before, well, why do helicopters sit in the right seat where, you know, fixed wing, they're in the left? And the reason is kind of simple. Most people are right-handed. So out of the two controls, the collective and the cyclic is where the pilot pretty much has to keep their hand on the wheel at all times. Okay? But where the radios and different switches are in the center of the helicopter. And so the pilot can usually set the collective and then fly just with the cyclic, but then they have a free hand with the left to be able to operate the controls that are in the center. Whereas if they're in the left, you know, they're flying with the right hand, it's really difficult for them to release that hand to activate that. Most helicopters are designed to be flown from the right seat. All right. Cyclic pitch, synchronized, okay, boosted controls. All this is that, you know, very small helicopters in that, they just have mechanical linkages. It's very similar to, let's say, the Cessna 150's rigging. The pilot pulls back, it pulls the cable, moves the elevator. On a helicopter, we move the cyclic. Generally, there's push-pull rods that then move the swash plate, all mechanically, all by the force of the pilot. But as the aircraft gets bigger, rigidity in space takes over, yeah, and that rotating disc doesn't want to move. So you try to move it, it resists that. So they give boosted, meaning that they will then have hydraulic cylinders to be able to move the swash plate in accordance with what the pilot wants. It's also designed so that the force can't go back to the pilot, that they just move it, the actuators move the swash plate, and we are good. All right, there's nothing really critical there. Torque compensation, I kind of already talked about it, you know, through the anti-torque pedals. Many people call them the rudder pedals. If you push on the right anti-torque pedal, what it actually does is it decreases the tail rotor's angle of attack, which produces less thrust or lift. And by doing that, the torque of the main engine or the rotor blades makes the nose go to the right. When you push on the left pedal, you increase the pitch of the anti-torque rotor, which pushes the tail to the right, making the nose go to the left. We have all different types of tail rotors. Typically, you know, there'll be an open rotor, okay? But in this case, you may have seen the helicopter that like the Coast Guard uses quite a bit, which is the Dolphin. It has what's known as a Finstron tail rotor. Basically, it's a big fan with, you know, a ductwork and then variable pitch blades. Now, one of the biggest dangers on helicopters is the tail rotor, okay? In that you lose the tail rotor, you lose control, and you're going to, you know, crash. All right. So this is why a lot of times, if the tail rotor is exposed, many times there's going to be a very big metal bar that kind of goes down. And the reason for that is when they come into land, if they come down with the tail down, that bar prevents the tail rotor from hitting the ground. Military, you know, use a lot of helicopters. And the great thing about helicopters is we can hide behind things, you know, bushes, trees and stuff. Well, the problem was with the tail rotor, you back up, you hit a tree, the tail rotor's gone, you're going to crash and such. So they came up with what is known as a NOTAR. A NOTAR stands for no tail rotor, okay? And what it is that they have basically the tail rotor inside at the transmission. And all it does is blows air out of the rotating nozzle. And so these blades are also variable, okay? So if you want to go to the left, it increases the pitch of these, thus pushes more air out to the left, making the tail go to the right and the nose go to the left. If we decrease the amount of air coming out, then the tail goes to the left and the nose goes to the right. Are we good there?
Yep.
Did Jaylene ever make it back in?
Yeah, I'm back, Bob.
Oh, okay. Do you have your question?
Yeah, it was just a quick question on the blades. You said that the collective, do the blades actually stop in midair?
Do they stop? No. The
Like
collect-
they
No.
stop rotating in midair?
No,
Okay.
no. I don't know how or what I said to make you think that. The collective, right, is a way that the pilot, when they lift or raise or lower the collective, it does the same thing to the pitch of the rotor blades. So if we pull up on the collective, all the rotor blades angle of attack increases
Okay.
so that we go up. If we decrease it, then the blade angles decrease and thus we produce less lift. Maybe it was when I talked about the throttle.
Mhm.
With the throttle on the collective, we can set the engine power setting, okay? But the thing is if we're doing that on the ground, we're setting the RPMs. That's how I'll explain it. We turn the throttle to get a given RPM, let's say 2000 RPMs, all right? Well, the problem is that when we pull up on the collective, the pitch of the blades will increase, which now the engine has a harder time to turn the rotor blade. And so the rotor blade would actually slow down,
Okay.
okay? So when the pilot pulls up on the collective, that will add more fuel to the engine to produce more power so that the RPMs can remain the same.
Got it. Thank you.
Thank you for the question. I think you're the first person that had a question really almost all term. Okay. All right, it's going to be break time, so we're going to take a break. We don't have much more for the helicopters to go. All right. We're going to hit that when we get back, and then we'll do the review over A and B and then see if anybody else has any questions. Thank you again, Jaylene.
No problem.
No questions. All right, I'll be back in 10. All right. We're back. All right, so we talked about the NOTAR, keep in mind, means no tail rotor. Okay, I gotta tell you one little story on the NOTAR. Some NOTAR helicopters, well, in this instance, one of the news agencies down here, I don't remember if it was channel 4, 7, 10, 6, whatever it was. But something happened down in Miami, and the news crews had their helicopters, checking out whatever the news story was. When they were returning, the helicopter pilots kind of were racing each other, having fun as helicopter pilots will do. Well, one of the problems is that one of the helicopters was a NOTAR. And the NOTAR helicopter had a kind of a bad flaw in it. And what it was that as you're going forward, no problem. But if you pulled back the cyclic, to kind of stop the helicopter, the retreating blade would dip down so far. And when the pilot, kind of overdoing the limits of the helicopter, when they pulled back, the retreating blade came back and cut its own tail off, and they crashed, burned and died. But that was kind of crazy when that happened quite a few years back. But anyways, stabilizer systems. Okay, this is where Bell helicopters, or the inventor of the Bell helicopters, Bell, came up with a stabilization system. Here's the thing, and I'll try to use this, okay? We got that rigidity in space. The rotor blade wants to do this. But if there's a gust of wind that hits the body of the helicopter, all of a sudden, we could lose total control of the helicopter. So what Bell came up with is a bar that rides underneath the rotor blade. It spins with the rotor blade, but keep in mind, it's perpendicular to the blades, okay? And they're also hinged, okay? So here's the rotor blade, and here is the Bell stabilization bar. Now, the Bell stabilization bar is what's going to try to stay level, rigidity in space. Now, what happens is if the helicopter tries to move like so, the bar, can you kind of see, is acting or staying level. So when it goes like this, it stays level. By it staying level, the link rods then, up here, pitch control links, because the blade got closer to the bell bar, it increases the pitch of that blade, thus aerodynamically uprights the rotor. Wow, that was hard to, I'm thinking it's very hard for you to understand that. If the rotor blade tilts because the helicopter moved over, the bell bar, or the bell stabilization bar, stays level. I didn't want to try to draw it, but okay. And there's the bell bar. If the helicopter tries to tilt over, the bell bar stays horizontal. The link rod then here, because the blade got closer, this blade, the angle will increase. This one, the angle or the pitch will decrease. So aerodynamically, this side will create more lift than that side, uprighting the helicopter. Please let me know if you just get the concept slightly.
Yes. So
Okay.
it's like the stabilizing bar, right?
Yes,
At a different location.
Right, it's underneath the rotor blades. It's going to try to stay horizontal all the time. If the helicopter moves, it uprights the helicopter by changing the pitch of the blades.
Okay.
Okay, now, here's the problem with it. Okay, if it works really efficiently, right, and the pilot wanted to go forward, okay, well, the bell stabilization bar would counteract what the pilot's doing, and they wouldn't be able to go anywhere, all right? So that's why they have what's called dampers. The dampers allow us, like if I do this, if I try to change something real fast, you can see I lose control. And that's what the stabilization bar would do. It prevents the rapid change, okay? But if I go nice and slow, then I have no problem. And the bell stabilization bar will also follow the rotor. It's just when there's a quick change, the stabilization bar is activated. And that's what the purpose of the dampers are. Okay, the rest of the material, offset flapping hinge, stability, autopilots, autopilot's an autopilot, it flies the helicopter by itself. So we are now on page 177. And they talk about helicopter vibration. Two different types of vibration. We have frequency ranges, okay? Well, we have two types of vibration. We have frequency and modes, all right? The frequency, we could have a high or a low frequency vibration. Many of you know, like a Twitter or bass. Bass is a low frequency, the Twitter of, say, a speaker is the high frequencies, okay? Well, many times a pilot will feel vibrations, okay? If the vibration is a high frequency, this usually indicates that something spinning very fast is the problem. So a high frequency vibration is usually going to be associated with the tail rotor because the tail rotor spins much faster than the main rotor. On the other hand, a low frequency vibration deals with something that's turning slower, and that would be the main rotor. So if you ever become a mechanic on helicopters and a pilot comes up to you and says, hey, I'm feeling vibrations, you could say, okay, well, is it a high frequency vibration, like a buzzing that you feel? Or is it more of a thumping, boom, boom, boom? Oh, it's a high frequency. Oh, okay, now you can kind of start looking at the tail rotor and drive shaft for the tail rotor. That would most likely be the cause. Whereas if it was a low frequency, then you would start looking into the main rotor system, okay? Now, there's also what they refer to as modes of vibration, okay? And there's a horizontal mode that, say you're hovering and you feel like you're swaying back and forth. Well, that is generally caused because one of the blades is heavier than the others, meaning that they're out of balance. So very similar if anybody has any ceiling fans in their house. If you see the ceiling fan moving horizontally, going, back and forth, that usually indicates one of the blades heavier than the other. And so you would have to do a check on the balance of the rotor blades, okay? And on some helicopters, there are attachments. And that's no. I don't see it on the. Oh, there they are. There's weights that can be adjusted to balance out the rotor blades, okay? If the mode of vibration is vertical, kind of that helicopter's kind of hopping up and down, this is usually an indication that the blades are what's called out of track. What that means is that, the blade angles are not equal as they rotate around, okay? So in that case, we would do what's known as a blade tracking. And that is to check, the path of each blade. Now, there's a couple different ways to do blade tracking, follow manufacturer's recommendations, but in this case, they're using a strobe light. And they put on reflectors on each of the blades. Let's say we just have two blades. You'd put red on one, green on the other. And with the strobe light, what should happen is timed with the engine, you will see a red dot, and then you'll see a green dot, okay? And they will superimpose onto each other. If the blades are in track, they both will, the red and the green dots will kind of overlap each other. If you see red higher than green or green higher than red, then the blade is said to be out of track. And then what we need to do is check the blade angles or the blade pitch and make the proper adjustments so that when the blades are rotating, they are in the same relative position. Are we good there?
Yep. Yeah.
Okay. All right, I got another quick little story. First time I seen a helicopter getting its blade tracked was actually here, because just on this side of the field, the Florida National Guard was here, and they had a bunch of UH-1 Huey helicopters. And my boss comes to me and goes, "Oh, Bob, you got to see this. They're going to do a rotor blade tracking on the helicopter." And he goes, it's wild. So a guy comes out, and what the guy has is a super long pole, and it has a piece of leather that's on kind of springs. And what the person does is there's a helicopter pilot that's actually running the rotor blades, and the rotor blades are at power. They've put chalk on, different colored chalk or paint on each of the blades. And then this gentleman had to lean the leather strap in until the rotor blade hit that strap. And then they pull it down to see, did the two colors hit each other, or was there a difference between the two? Talk about something scary, trying to put a big long pole into a running helicopter blade. It was like, they're nuts. So it's much better and easier, safer to do with the strobe lights. All right. So that's that. That's helicopter power systems. Yes, helicopters can use reciprocating engines, but keep in mind, reciprocating engines are generally heavy for the amount of horsepower that they can put out. The helicopter really got into its own when the turbine engine was developed. With that, we have a lightweight, very high powerful engine that likes to run at a very constant speed, okay? And so turbine engines do a fantastic job. I'm not going to go heavy into this because I don't know how many of you have had power plant 1 or 2, but the type of turbine engine that's generally used for helicopters is what's known as a free turbine, also known as a power turbine. Now, most turbine engines, like for fixed wing aircraft, what they do is they take air in, they heat it up by the combustion process, and send it out back at a much greater velocity. And so if you throw something back, you go forward, all right? Well, in a helicopter, we need to convert this into rotational motion. So this is an example of a helicopter turbine engine. This happens to be what's known as an Allison 250. A lot of the Bell helicopters, a lot of helicopters use this. So coming in, we have the compressor that compresses the air. The air actually goes through an external pipe to the combustion chamber, okay? So now this is where the fuel and air is mixed and burned. The fuel and air then comes through, okay, and goes out the exhaust. Now, we have to have energy to turn the compressor. So the first stage of the turbine blades are connected to the compressor. So this turbine turns the compressor that compresses the air for combustion. We then have a second set of turbine blades. So the hot exhaust gases now turn, in this case N2, I don't want to get into that, but through these sets. But now this set is going to a gear drive and is not connected to the rest of the engine, okay? What this means is that we can start the engine, we can actually stop this from turning with what's known as a main rotor brake. We can hold that stationary, the engine can run because, you know, N1 is not locked up and turns the compressor. When we release the rotor brake, then N2 can start spinning and put out the power. But now, usually this goes to the transmission, but it's known as a free turbine. And the reason why it's called a free turbine is because this turbine is free of the engine. Are we good there?
Yep.
Okay, I'll say you are. And really the last is what I've already talked about, and that is all helicopters, the main rotor, where it connects to the transmission, okay, has to have what's known as a freewheeling unit. Basically, we have a clutch, okay, that when the engine tries to turn the rotor blade, the clutch locks up to turn the rotor blade. If the rotor blade turns faster than the drive, then it's a freewheeling unit. It's very similar to like a 10-speed bike, meaning a bike with gears. If you notice, you can push the pedal that turns the rear wheel. But if you stop pedaling, the rear wheel keeps spinning. All right, and that's the freewheeling clutch. Folks, unless you have questions, I am done with the helicopter section. Are we good?
Yes, sir.
Yes, sir.
So once again, tomorrow, you know, the final for assembly and rigging will be open starting, I believe, at, I'll just say 7:30. Yes, you do have until Monday to complete the final, okay? Also, keep in mind, make sure everybody gets their stuff done, all right? I cannot stress that enough. Please, you've had plenty of time to get it done. You know, if you've waited till the last minute, I'm sorry, but you gotta get it done. You have the rest of today, you have all day Friday. If you got to, Saturday, Sunday, and Monday, you know, there is no excuse for not getting all of it done. All right, with that, I do want to review over, all right, and I'm gonna try to do it kind of quickly and stuff. All right, going back from page 1, we have 2 types of aircraft construction. We have the truss type and we have the stress skin. 2 types of truss type structures. We have Warren and Pratt. 2 types of stress skin. We have monocoque, semi-monocoque. Out of the 2, which one has a substructure That is known as the
And,
semi-monocoque. All right. We talked about the airfoil sections or airfoils. As we said, if the shape above and below the chord line are exactly the same, we say that's known as a symmetrical airfoil. Symmetrical airfoils are generally going to be used for 3 different types of aircraft. Number 1, rotor blades of helicopters. Number 2, acrobatic aircraft. And number 3, supersonic aircraft. All right. For the reason for the helicopter is a symmetrical airfoil. As the angle of attack changes, the center of pressure does not change. Therefore, produces less stress on the rotor blades. Okay. We talked about the asymmetrical airfoil being the airfoil that is used the most, right? And we came up with a very basic idea of how the airfoil produces lift. As air flows over, we say the velocity increases and the pressure decreases. Underneath, we have a relatively high pressure, high goes to low and lifts the aircraft up. And that's a very simple way to explain it. But what we need to know is that there's also Newton's law. For everything that goes up, something has to come down. And in this case, it's the air, because we have high pressure above that low pressure. And so this high pressure air comes down, and that is referred to as the downwash. Okay. We then talked about the lift formula. Not that you need, I'm not going to ask you a test question, please tell me what are the 3 things of lift, blah, blah, blah. But the lift formula is the coefficient of lift times the dynamic pressure. And the dynamic pressure is actually the density of the air time, or 1/2 the density of the air times the velocity squared, times the area of the wing, okay? Now, the area of the wing and the dynamic pressure, okay? But the coefficient of lift is basically the aerodynamic shape of the airfoil, and the angle of attack is what determines the coefficient of lift. Now, once the wing has been developed or built, we can't affect it anymore. So the pilot can control the lift by controlling the angle of attack. When we increase the angle of attack, the lift is increased. We decrease the angle of attack, we decrease the lift, okay? Now, the problem is that at a specified angle of attack for any given airfoil, the air will no longer stay attached to the wing and separate. And this is known as a stall. The angle of attack at which an airfoil stalls at is known as the critical angle of attack. Airframe 2, you'll go into the warning devices for that, but basically there's a stall warning. Small aircraft usually also will have what's known as a stall speed. Okay. Remember with the airfoils, the 2 angles that are most important to remember is angle of attack and the angle of incidence. The angle of incidence is that angle formed between the chord and the longitudinal axis, whereas the angle of attack is that angle formed between the chord and the relative wind. Does anybody have questions on that? All right. Next page, flush area, truss type wings. Let me get rid of this. I'm going to hit some of the pictures now. I gotta go back, way, way back. All right, so flush rivets in this area, because any protrusions in that could actually cause a stall. As far as this part goes, not too much. Keep in mind, what is the name of a wing that has no external bracing? And the answer to that is a cantilever wing, okay? Here we looked at the large or commercial airliner wing, right? We have the leading edge flaps here. We have the the slats. We have an outboard and an inboard aileron. Keep in mind, as far as the ailerons go on this, if it has the two sets, outboard and inboard, then the outboard ailerons are considered the slow speed ailerons, and the inboards are known as the high speed. During slow flight or when the flaps are extended, depending upon the aircraft, both ailerons will operate together. When the flaps are retracted and or the aircraft reaches a certain given speed, then the outboard ailerons are locked into the neutral position, and only the high speed or inboard ailerons will function, okay? We talked about the trailing edge flaps, and then we have the spoilers. The spoilers are there to reduce lift. They kind of first were put in so that during landing, we could destroy the lift of the wings so that more weight was on the wheels, thus the brakes could be more effective, okay? But eventually we learned that, hey, not only could we use the ailerons to roll the aircraft, but we could use the spoilers to help control the aircraft, to slow it down for quicker descents and such, okay? Here, the main thing was we have the winglets, and keep in mind, the winglets are there to reduce what is known as wingtip vortices. We have a pair of wing fences, and the purpose of the wing fences is to redirect the airflow over the wing so that the flight controls are more effective, okay? Here we have what's known as vortex generators. And the vortex generators are there to help reduce or prevent what is known as a shock-induced stall. Basically, to help prevent a high-speed stall. And that is, we're going so fast that the air can't stay attached to the airfoil and thus separates, okay? And the vortex generators help prevent that from occurring. Here again, we see a wing fence, but then we see the different positions of our horizontal stabilizers. Here we have a push-pull or a Skymaster 337 with a centerline thrust. Mainly that was to help reduce the danger of asymmetrical thrust when a multi-engine aircraft was to lose an engine. Here we have a truss type structure, nothing special there, retractable landing gear. This is the Lake aircraft that when we were talking about the symmetry check, this aircraft in its maintenance manual actually had a symmetry check, which was like, okay, go from the nose or from this point here, go out to the left wing, go from this point, go out to the right wing. And the reason why this aircraft actually had one in their manual is because it lands in water and the pontoons, and hitting that water can put a lot of strain on the fuselage, and with the skis and such. In section B, we talked about the controls of the aircraft and the three axes. Remember, we have the longitudinal axis, the lateral axis, and the vertical axis. What rolls the aircraft about the longitudinal axis is the ailerons and is known as lateral control. What pitches the aircraft about the lateral axis is the elevator, and the elevator gives us longitudinal control. Then we have directional control, which is done by the rudder that rotates us about the vertical axis. Okay. All right. Then we talked about stability, and we said that two different types of stability. The initial response of an object once it has been upset is known as its static stability. Whereas after the initial response, what happens is known as its dynamic stability. We do want to build our general aviation, our commercial aircraft with a positive static and a positive dynamic stability. And what that would do is that the aircraft, if it is upset by outside forces, it will regain and fly at the attitude that the pilot has trimmed the aircraft to be. All right, not going to go heavy more than that. Oh, except for this one. If the aircraft has a positive dynamic stability, what type of static stability must it also have? And the answer is positive. All right. All right. So we talked about the stability about the axes. What makes an aircraft longitudinally stable? And that is the center of gravity is forward of center of lift. Okay. And the horizontal stabilizer. What makes an aircraft laterally stable? And the answer is the dihedral. The dihedral is where the wing tips are higher than the wing roots, and that is known as the dihedral. We said that low-wing aircraft require a greater dihedral than, say, compatible or comparable high-wing aircraft. The high-wing aircraft doesn't need such a large dihedral for two reasons. Number one, what is known as the pendulum effect. You know, with a high-wing aircraft, we have most of the weight underneath the wings. So if the aircraft does roll, the weight will want to upright the aircraft. The other thing is what's known as aerodynamic blockage or fuselage blockage. And that when the aircraft rolls, it's going to slide towards the low wing. The fuselage will block the air trying to hit the highway and thus reduce its lift. Okay. And then what makes an aircraft directionally stable is the vertical fin. That if the aircraft yaws, air will hit it and straighten out the aircraft. From there, we talked about the control systems with the longitudinal control, which is pitching the aircraft up and down, would be done by the elevator. Keep in mind, the elevator, if we pull back, the elevator goes up to make the nose go up. Down. If we push the nose down, the elevator goes down and the nose will go down. And that one I think is pretty easy. The rudder also. We want to go to the right, we push on the right rudder pedal. The rudder is deflected to the rudder, or to the right, which then pushes the tail to the left and the nose to the right. The ailerons are kind of the more difficult one, in that if we want to roll the aircraft to the left aileron goes up, the right aileron goes down. By the right aileron going down, it creates more lift, so the right wing will go up. The left aileron going up will reduce the lift and push that wing down. There's a problem though with this arrangement, and that is when the right aileron goes down, producing more lift, it also produces more what's called induced drag. And the aircraft has a tendency to yaw in the opposite direction of the roll. This is known as adverse yaw. Because they needed to minimize adverse yaw, an aircraft may have one of three different ways that the engineers figured out how to minimize adverse yaw. The first way is what's known as differential travel, in that the down aileron will travel less than the up aileron. The up aileron will travel a further distance, thus creating more parasitic drag to balance out the induced drag created by the aileron going down. The second way is what's known as a Fry's aileron. A Fry's aileron, the hinge is aft of the leading edge. When the aileron goes up, the trailing edge goes up, the leading portion of the aileron will stick underneath the wing and thus create additional parasitic drag. The third way is what's known as a aileron rudder interconnect spring. And that when the pilot rolls the aircraft, say to the left, there's a spring that connects the aileron cable and the rudder cable, so the rudder would be pulled to the left. And thus, the aircraft would roll and turn to the left. Any questions there?
No.
Okay. All right, so we killed off quite a bit so far. Okay, tabs. All right, tabs are devices that aid the pilot in one of two ways. It could be used to aid the pilot into maintaining a specific attitude, or it can be used to aid the pilot in movement of the control. If it's a trim tab is there to help hold the airplane in a specific attitude, okay? A servo tab aids the pilot in movement of the control. Now, because they're both tabs, they kind of do the same thing, but they are slightly different. Some tabs can do both, and that is help trim the aircraft and also act as a servo tab. If a tab has both functions, trim and servo, then it's known as a balance tab. Okay? There's one special, all tabs, except for one, moves in the opposite direction of the control that it's attached to, okay? And this is known as an anti-servo tab. An anti-servo tab moves in the same direction as the control and are usually found on what's known as a horizontal stabilator. And that is the horizontal stabilizer and the elevator are joined as one, known as a stabilator. And with that, they use what's called an anti-servo tab. All right, flaps, which are high lift devices. Okay. Keep in mind, in trailing edge flaps and leading edge flaps, what is the purpose of flaps? It's to increase lift at slower airspeeds. There are four types of trailing edge flaps. We have the plain, we have the split, the slotted, and the Fowler. Out of the four, the one that increases the surface area of the wing before it increases the curvature or camber of the wing is known as the Fowler flap. Okay. We should also know there's two types of leading edge flaps. The two types of leading edge flaps is the Kruger and the Droop. Remember the 727 has the Kruger. We can kind of remember that name because of Freddy Krueger. All right. There's the triple slotted Fowler flap. Okay. Now, another leading edge device is known as a slot or a slat. They do the same thing, but the difference between a slot and a slat is a non-movable opening in the leading edge of the wing. A slat has an opening, but it moves. So during standard flight, the slat is retracted, but then we can extend the slat to open up the slot. Slats and slots are for the purpose so that the airfoil can reach a higher angle of attack before it stalls. That's all, okay? Are we good there? Okay, all right. Sometimes engineers screw up or they find something that was unexpected. In this case, what they found was that the whole wing was stalling, or wrong portions of the wing was stalling before the area that they wanted to stall. So to promote a stall in specific areas, they can install what's called a stall strip. And that's all it does. A stall strip promotes a stall, say, before the critical angle of attack. We talked about the wingtip vortices and all that fun stuff. Here we have a canard, right? We've already gone through the large aircraft, so nothing more there. There's the Kruger flap, the dihedral, angle of incidence, bubble protractor, cables. I got nothing really. The type of splice that we no longer use, either the Army Navy 5-tuck splice or the Robley roll, right? When doing a nicro press sleeve, we always want to crimp the center first, then next to the eyelet or the thimble, and then next to the tag end. To make sure that the has been installed properly, be it the MS or the nicro press, we use what's called a check gauge or a no-go-go gauge. Okay. Here we're just seeing the different cables. These are the MS, right? Which are a swagging tool is used to crimp down, if you will, or swagging, you know, the barrel onto the cable. Okay. Again, a no-go-go gauge is used to make sure that it is properly. Inspecting of the control cables, you know, we want to do a visual inspection, but what we have to understand is the cables many times are pre-wound. So if the cable wires actually break, we may not be able to tell this. So what we like to do is take a rag, run it along the cables to see if any cables will, or the fine wires will actually snag the rag. In some cases, we loosen up the cable and we're going to want to bend it to see if any of the wires come up, okay? Different devices to help protect the structure from the cable and vice versa. We have rub strips, spare leads and such, but where a large change in direction is required, then we use pulleys, okay? They're just, always, you know, we follow the manufacturer's recommendations when we're rigging and with the use of a cable tensiometer. And keep in mind, always when you're doing the cable tensiometer, check to see if the cable tensiometer has been recently calibrated, and always follow the calibration chart, because what we see here, kind of 30, does not always necessarily mean that we got 30-inch pounds. It could mean, you know, lower or higher than that number, so we have to follow the calibration chart. Okay, we talked about the safety wiring. On the turnbuckles, we can see this one has a groove, right? And that would indicate the left-hand threads. Push-pull rods, bell cranks, and that was it.
Good job.
I'm done.
Thank you.
Oh, thank you. I mean, it's hell, but is everybody okay then?
Yes, sir.
Yes, sir.
Yeah.
I got nothing else unless you have questions, you know, please feel free to ask. Once again, I'll just finish up by saying, you know, review over the material, try to work on, you know, the online assignments, make sure that either, you know, tomorrow, Saturday, Sunday, Monday, complete everything and do the final. The final, I believe, is 30 questions again. There's 20 FA and then 10 Bob questions. All right. Get that done. The sooner you get it done. Hey, if you worked on it for the rest of today, all you'd have to do is tomorrow, take the final, and you're free to Tuesday. Okay? Because then on Tuesday, we're going to be lecturing over landing gear. All right. And then most likely on Wednesday, Thursday, we're going to come in to get our project going. All right. And then we'll see what we do from there. Good?
Sounds good.
Sounds great.
Okay. All right. Thank you very much. Have a good day.
Thanks, Bob.
Yeah,
You too, Bob.
thank you.
Have a good one.
You too. Morris. Hey,
Yes,
I said his name right. I'm sorry.
yes,
Morris, I actually said your name right.
yeah,
How you feeling?
I'm doing better.
You doing better? Okay, good. All right. Yeah, I was happy to see that you joined the class, you know, that you were able to join the class again, not that you haven't joined, but very good. All right, so we got a few more days before we come into the shop, and I know we can talk about, you know, the other things later, all right?
Yes,
Okay, all right then, I'm ending the meeting. Thank you all.
thank
And if
you.
you got any questions, you know, you can always email me. I will be checking my email. But please use the Broward College email, not D2L, because this weekend I'm not going to be near a computer, but I'll have my phone.
Yes,
Okay? All right then, be good. I will send out an email later today to say, you know, what I've repeated here and to have the Zoom meeting on Tuesday. We're gone.
All right.